API. Today, this system it's a service that processes billions of events per day. We insert about 10 million rows per day. And it's a system that has very strict performance constraints. So what I'm going to do is I'm going to explain really how we design our system from the ground up, how we design the schema using Postgres, obviously, and using Citus data. So first, just a little bit for context, what is Algolia? What do we do? We are a hosted search API. It means that we provide search as a service. And the way it works is you, as a developer, you send us your data, we index it in real time, and then you use our API to provide, to get results in real time. Why would you use a service like us? Well, we take care of all the infrastructure, we scale with you, and we provide, as you type speed, we are a very fast search engine. You should expect results in a few milliseconds. We provide relevance tool, we are typo-tolerant by default, etc. And we really strive to provide the best developer experience possible. We are developers, we build a service for developers. We want this to be a delightful experience. You may not know us, but you might still have used us under the hood. If you are familiar with Hacker News, if you search on Hacker News, you have used Algolia. If you've recently been searching for video streams to watch on Twitch, you have used Algolia. And you've seen what I mean by having an instant search experience where you get results at the very first keystrokes. And finally, just to share more context about the scale at which we operate, which will be useful for the remainder of this presentation. Today, our API processes roughly 200 billion calls per month. And among those calls, about 40 billion or between 1 and 2 billion calls are search calls. And among those search, we also provide our customers with analytics, which is what this talk is about. How do we process all those events to provide an analytics API and a dashboard to our customers? So what I'm going to do is I'm going to show you what we build, and then I'm going to dive into all the journey into how did we build this system. So we'll talk about what tools we consider for the job, where we are coming from, and ultimately, how did we design, how did we leverage Postgres and Citus to achieve what we needed. So this is a screenshot of our dashboard, of the Hacker News dashboard, actually. So this is something we provide to all our customers. So we have thousands of customers, and they all get access to their own dashboards. Why I'm showing this is to show you the kind of metrics we are going to be interested in surfacing from the system. We have actually a few kind of different metrics. We have global counters, how many search has been made in the last day, week, month. Distinct count, how many unique users interacted with your system. And then we do a lot of stops. What are the most popular searches? What are the most popular documents retrieved by the system, etc., etc. And so it was critical that we find a data store that could provide us with this kind of metrics as efficiently as possible. So for context, Algolia had analytics for many years. At the beginning, we were using Elasticsearch, so we had a self-hosted Elasticsearch cluster, which worked pretty well at that time. At that time, the scale we operated on was maybe 500 million calls per month. Fast forward to today, we do 80x that. So we started to have some issues scaling this. So we did some sampling, and then it was becoming a burden to maintain. We had a hard time actually achieving the performance we needed. And we also wanted to move away from a very flat schema to a more like relational database. So we started our quest to find something that could fit all those needs. So we started by listing all our requirements. The main one was we wanted to have sub-second response time. We are not powering a warehouse. We are powering a dashboard. When you connect to your dashboard as a customer, you don't want to have to wait minutes to get your result. So we want to achieve sub-second response time. The data should flow is constantly flowing into the system. This data needs to be reflected, maybe not in real time, but let's say a couple of minutes would be acceptable. we give our customers a lot of retention. Our largest customers have maybe a year, if not more, of retention. So we are going to need a system that can ingest billions of events per day, but then we need this system to be able to provide metrics across potentially a whole year. And we still need this to be done in sub-second. We need a system that could scale with us. At Algolia, our growth is basically, we double every year. So we need a system that what we build today, we don't want to have to redo it the next year because we have outgrown the system. So we are looking for a system that will be able to scale ideally just by adding more machines. And we wanted something that was hosted because while we do maintain our own search infrastructure, we don't want to have to maintain other services like this. It's not our job to maintain databases. Okay. So we started by evaluating the usual suspect in this area. So since we are looking for something hosted, we did not consider stuff like Druid or Pinot. The first one we looked at was BigQuery. We didn't really use it because we realized that achieving sub-second performance with BigQuery was actually very hard, if not if possible at all. Pricing was also an issue because with BigQuery you pay based on the amount that you scan, so it's very unpredictable to power a public API with BigQuery in terms of pricing. We looked at Redshift. Again, very good for data warehousing, but when you want to achieve sub-second response time, there are some kind of workloads where it's going to be prohibitively expensive to do it with Redshift, as we will see with Citus. Basically, the lack of some data types and some sketch algorithm that we can do on Citus but not on Redshift made Redshift not a good fit for us. So now I'm going to reintroduce Citus, and we'll see how we actually leverage Citus and Postgres to achieve what we need. Okay, so what is Citus? So it's been introduced a few times already. It's a Postgres extension. So here the main keyword is extension. It's not a fork. What does it mean? It means we get everything Postgres offers and more. Joins, indices, native partitioning, statistics, everything we get out of the box. It also means that we are always running an up-to-date version of Postgres. When we started this project a year ago, we started with 9.6. When PG10 was released, we updated to PG10, and now we just can't wait to have PG11 to use a few of the upcoming features. And I'm sure that as soon as PG10 is released, we'll be able to update within weeks. And so what does it do? Well, Citus allows us to distribute our databases across workers, as many workers as we want. Which is great because we are in a multi-tenant context. We have thousands of customers that don't share anything. So being able to distribute all this data across as many workers as we want is really helpful in our case. Citus also allows us to scale up and out in the blink of an eye. Scaling up the machine, swapping them for larger machine is as easy as clicking the button in the UI, and scaling out is as easy as requesting more machines and rebalancing the shards, basically. In terms of infrastructure or architecture, how does Citus works? Well, it's a classic master-worker schema. You have so the master is called the coordinator here. The coordinator runs the Citus extension. It contains metadata about the whole system. And then what we do is we're going to create table and tell Citus to distribute them along all the workers that we have in all the shards that we have. So the worker is a node, and the shard is a vanilla Postgres table, basically. So a table that so when we connect to the coordinator, we connect to it's as if we are connected to a single node Postgres instance. But then under the hood, the table is actually distributed in all those shards and in all those nodes. So what this means is that the queries will be parallelized across all the shards if is needed, or if we are in a multi-tenant architecture and all the shards contains only a few customers, if we need to have a query for just one customer, we just go to one single shard, which means we can have many customers querying their database or the system at the same time, and this is parallelized across all the shards. All right, so this is the basis, but now how do we actually achieve sub-second response time? As I said, we are going to insert billions of rows or dozens of billions of rows into the system. Even with parallelism, there is so much that you can achieve. As a rule of thumb, with Postgres, you should expect roughly 1 million rows aggregated per second per core. So yes, you can parallelize that as much as you want, but at the end of the day, if you want to get sub-second response times across billions and billions of events, that's going to be a lot of cores. So what we do is we actually use what we call a rollup approach. We're going to take all our data and we're going to pre-aggregate it based on some predefined time ranges and some predefined dimension. So rollup is basically a fancy word for pre-aggregating the data based on dimension and time series. What I'm going to do now is I'm going to walk through the workflow. How do we actually instrumentalize Postgres to do this? So we'll see how we ingest the data, how do we scale the insertion. We'll see how we roll them up, how we architecture the queries at the end to get the data out of the system to our customers, and then a few words about how we delete those events. All right, so I'm going to start with a simple example. If you remember the dashboard I showed at the beginning, we are interested in surfacing a few queries. We are going to be interested in surfacing the number of queries we've seen. We are going to be interested in surfacing the unique number of users we've seen. And we're also going to be interested in surfacing the top queries that we've seen for a given time range. Day, week, months, whatever. So we're going to create a very simple schema. The first thing we're going to do is we're going to tell Citus that we want to distribute that table. So for that, it's a simple SQL function, create distributed table, name of the table, and name of the column that will be used as the partition key. So here we are telling Postgres or Citus that we want to shard based on the app ID, which is the tenant or the customer in our case. How do we scale the ingestion? We're going to need to push all this data into this table. How does it scale? So the first thing we do is obviously we use copy, not insert. We're going to do it in parallel. We're going to have many services that push batches of rows into the system. This one might sound obvious, but we're going to try to not add indices or as few indices as possible on our row events table, the queries table. And this is actually easy to do because, as we will see in the next few slides, we are not really going to query that table after it's rolled up. So we don't need to optimize for read for that table. Something we've been doing and that showed a lot of substantial improvement is to turn synchronous commit to off. By default, with Postgres, or at least with Citus, this setting is turned to on, which means that the transaction will only return after the write-ahead log has been flushed to permanent storage, which is great if you want guarantees that you will never lose data, basically. If you're a bank, that's probably what you want. In our case, we can actually accept having our transaction returning before that happens. The trade-off is our transaction will return faster, which means that they can return before the write-ahead log has been flushed to disk. So the trade-off is faster transaction, but if Postgres crashes right after the transaction has finished, but right before the wall has been committed, we will lose that data. In practice, for us, this is a completely acceptable risk, especially considering the substantial gain in performance. And so how far can we go? How much rows can we insert per second? I'm putting that number here. This number comes both from benchmark from Citus, and we've also been able to get quite close to that number, 7 million rows per second, which is 600 billion rows per day. In practice, this obviously depends on the kind of machine you use. To achieve this number, there was no replication, no index, and obviously a table distributed across a couple of workers, and a very compute-heavy coordinator node. But this is still to give you an idea of how far we can go. All right, so we've got the data into the system. Now we need to roll it up. We need to aggregate that data to get our metrics. So what we're going to do is we're going to create a roll-up table. The first thing to define is what's the time series on what timestamp are we going to aggregate the table. At Algolia, the first aggregation that we do it on the 5-minute ranges. That means that we take all the data for a given customer that we receive in a predefined 5-minute range, and we aggregate it. We could have used 1 minute, we could have used 1 hour, 1 day. It's entirely up to you. The trade-off is the more granular the time range, the smaller the time range, the more data you're going to keep at the end. And obviously, the coarser the time range, the more compression you achieve at the end. For us, 5 minutes was an acceptable trade-off. So we've got the time series, the time range, 5 minutes. Then we need to pick the dimension. Based on what are we going to group our metrics? In this simple example, we are just going to group on the app dimension. But in practice, in a real-life scenario, you will have probably many more dimensions. So you're probably going to end up with many more Rollup tables based on the dimension you want to surface. And then we have the columns that's going to hold the results of our aggregation. As I said, we want to surface 3 metrics: query count, unique number of users, and the top queries. So those are the 3 fields here: query count, users, and top queries. I'm going to explain very shortly what are those HL and JSONB fields. But first, what we do is, again, we're going to tell Postgres, we're going to tell Citus that we want to distribute that table per app ID. Both stable queries and Rollup are sharded on the same key, app ID, which means that they're going to end up on the same shard into the system. So when we're going to move that data for a given customer, when we're going to roll up that data, we will always be on the same shard. We will completely avoid network traffic when we do that. All right, so a word about hyperloglog and topen. So this is actually let me go back, the HLL type here for users. This is coming from an extension, also supported and maintained by Citus, which is the PG HLL extension. So those are sketch algorithms. HLL, which stands for hyperloglog, is a probabilistic data structure, probabilistic algorithm that allows for very fast, distinct, approximative distinct count. Topen follows the same logic. The goal is to be able to get an approximative top from an arbitrarily large set. The way it works is during the aggregation, the topen extension will accumulate events, will only keep a fixed number of items, and will keep only the top n at the end. So why do we use this? Well, first, because if you are aggregating over billions of rows, you don't want to keep billions of intermediary elements in RAM, basically. And also because those two structures, topen and hyperloglog, can be merged. If you've been computing your unique number of users using a selected distinct count for a given day, and you've been doing the same for the previous day, and then you want to answer the question, how do I do if I want the unique number of users across those 2 days? How do you do? Do you go back to your raw events and you recompute everything? That's very inefficient. Instead, we just take those two structures, we merge them, and we extract the cardinality. And you can do the same for topen. Okay, so we've got the rollup table ready, we've got the queries, we've got our events flowing into the system. How do we roll this up? Well, we use the insert into select statement. So we're going to group by our dimension, which is app ID, and we're going to group by our time range, which in our case is the 5 minute, the timestamp truncated to the beginning of the 5 minute range, so 0, 5, 10, 55. If you were rolling up by hour, you would just truncate to the nearest hour, etc. And in terms of the aggregation function, well, we want the count of user, of queries actually, so it's just a count. And then a bit more interesting for the HLL, what we do is we take our user IDs, we hash them, we insert them into the HLL structure, which is just a bit set at the end. And for the topen, we use the topen extension. We take all our queries, we put them into this set, and at the end of the aggregation, we're just going to have our top n, where n is 1000 by default, but that's configurable. And then basically what we do is we wrap that statement into a PG SQL function, and we call it whenever we need to roll up our data. So at the end of the aggregation, what we get is all our events for a given dimension, here the app ID, that we received for a given 5-minute range ends up being just this single row into the database. And that's where we get our compression, and that's where we're going to be able to achieve very fast queries at the end, because the amount of data that we ultimately need to scan to get our metrics is so small that it's trivial to just retrieve in milliseconds, basically. So one word about Topen again. Here, as we can see, Topen leverages the JSONB format, and our top is actually a JSONB field where the keys are our top elements, the values, and the values is the frequency. And Topen is going to help us fetch items from this top in sorted order. Okay. Before going further, I will stop to talk a little bit about idempotency. This is something we've been struggling for a while, actually. In our case, we need to be able to reprocess data. We need to be able to reprocess ranges of data. Why? For many reasons. First, our upstream queues may produce duplicates. We may receive the same insert job several times. We don't want that to produce duplicate metrics. Also specific to our use case, we always process logs for a particular time window, but we process logs coming from thousands of servers. And those logs, we may receive them at any time, actually. So it's possible we've started processing one range that's incomplete, and maybe a few minutes or a few hours later, what's missing is coming. And so what we want to do is reprocess the entire range. So we need to have a way to insert and compute those rollup idempotently. So what we do is, which is a bit brutal, but before every insert, we actually delete the data for the given range we're about to insert, and then we do the copy. For the rollup themselves, it's actually much easier because we can take advantage of the onConflict do update set clause, which means that we're just going to overwrite the rows into the table. If you don't need idempotency, if you have a system where you're just constantly appending, well, obviously you don't need to delete, and then you can take advantage of the onConflict clause to append to your rollup. So instead of overwriting your columns, you will just append to the count, append to the HL, or append to the Topen, which is supported by those algorithms. You can append a value to an HL and still get a distinct value at the end. Okay, so we are pretty much done. Now, how do we actually architecture, how do we design our queries that powers the dashboard or the API? The first thing to keep an eye on is that those queries, since we are in a multi-tenant use case or context, are always going to target a single customer or a single shard, which means that even if you have thousands of customers like we do querying the dashboard every day, it's still going to parallelize very well across all our shards. And so what needs to be done at the end is just a final aggregation. If you want your data, if you want to know how many queries you had for a given day, well, how many rows do we have in the system? Since we rolled up by 5 minutes interval, there is 288 times 5 minutes in a day, so that's 288 rows to fetch, which is very trivial, and then we do a sum at the end. A bit more interesting, how do we get the distinct count? We do the same. We take all our HL structures, we do the union, and we extract the cardinality. And same for Topen. We take all our intermediate Topen, we do the union, and then we tell, thanks to the Topen extension on API, we say, give me the top 10 here as I'm showing in this example. And what we get at the end is the values and the frequency sorted by frequency decreasing. So that's pretty much everything we are doing. There is also a word about deletion. We push dozens of billions of rows per day into the system. We don't need to keep them, actually, because as soon as they are rolled up, we can actually discard them because we are not going to use them to query to use them for our dashboard queries. In practice, I would recommend at least we still keep them for a few days in the system just so we get a quick way to run some debugging or analysis on maybe 24 hours of data. But after this is over, we can just remove everything from the system. We also need to delete we also enforce retention for our customers. So we need to delete data from our customers on a periodic basis. If a customer churns, hopefully it doesn't happen often, but when it does, we need to remove that data from the system, especially with this very nice regulation called GDPR. We can't just keep data forever. So the good thing with Citus is that delete are also running across shards, so we take advantage of the parallelization. And Citus also supports native partition, so we can also just drop table where it's applicable. All right, so I've shown the core of the system. This is pretty much everything we are doing. But there are actually more optimization that we do because even at the scale at which we operate, even by doing rollups on 5 minutes, at the end of the day, at the end of the year, that's still a lot of data into the system. So there are a few more things that we do to optimize this system. The first thing that we do is we actually further roll up the rollups. We keep the 5-minute rollups for a while, and then at some point we actually roll them up again into daily rollup. So we're going to scan those rollups, which is actually pretty fast. We never go back to the raw data set because it will take hours and hours. And we further reduce the granularity, which in our case is acceptable, to get daily rollups. And you could imagine doing this for monthly rollup or yearly rollup. This is obviously specific to each and every one use case, but in our case, we see a compression ratio going from 200 to 50,000x. That means that for every 15,000 rows we push into the system, at the end of the day, we keep one row. This one just for maybe useful, but since we delete a lot from the system, we have to vacuum. We do rely on the auto vacuum. Something that was a bit needed was to fine-tune the scale factor, so the auto vacuum is more aggressive. By default, it's 20%. We use, I think, 10% in production, so it's a bit more aggressive. And just to show that you can use Citus as you will use any Postgres instance, we also rely on statistics, which is a PG10 feature, and you will just do that exactly as you would do on a regular Postgres instance. Something that will inevitably happen, I mean, in an ideal scenario, all your tenants, all your customers will produce the same workload, and they will be evenly distributed across the cluster. In practice, that's not what happened. Especially in the SaaS industry, most of your customers will probably be small, and then you're going to have a few that are extremely large, and this will skew the cluster. So by keeping an eye on that and by identifying that, the idea is to find this skew and rebalance the cluster so that if you have too many big customers on the same shard, you actually split that on the same node. You split that so you even the workload. And to do that, it's actually pretty easy with Citus. It's just a simple command, either to rebalance the whole table across the cluster, or if you find that you have a shard that's way too big, you can actually move it to either its own node using isolation, or into an existing node, basically. But it's very easy to move shards around. And with, as long as your tables have a replica identity, this can be done online. That means that you won't be blocking neither read nor write. If you don't have replica identity, you will be blocking the writes. Okay, and this is my last slide, just to give you an idea of how the system is performing, what do we get, and what do we use in terms of hardware. Today, our main cluster use 6 nodes with 64 shards, so we have basically 10 shards per node. As I said, we are pushing roughly 10 billion rows per day. We are also deleting 10 billion rows per day. And to give you an idea of the compression ratio, the data that we push every day is roughly 1 terabyte. But after 8 months, the system has been in production for 8 months, the size of the rollups, including index and everything, is only half a terabyte. And this is how we achieve pretty good performance and at a relatively small price, because we don't need to keep all this data. And and so what we were looking for at the beginning was sub-second response time, and what we see is that the P99 for all our analytics queries are answered in less than 1 second. Something I didn't mention, but the limitation of this approach is that it only works if the compression ratio is high. It only works if the cardinality of your dimension is small enough that you don't have thousands or millions of dimensions to compute. This is something we're actually working on solving, so I hope in the future I might talk about that. But that's it. That's what I wanted to say. Thank you. And if you have questions, obviously go for it. Yes?
So then when you are loading raw data, you're saying you are using parallelized copy.
Yes.
So is that possible? Like, I suppose that depends on how you define your targeting scheme that you can parallelize, or is it totally independent? Like do you when you copy raw data, do you target just one? Let's say you design the table in target database that will load only by that copy, and then the other one you're just using another table to copy as well, and that enables you to be able to parallelize, or is it totally
So the question was, how do we? I mean, do we do anything specific regarding the copy? Or the parallel copy? We don't do anything specific. Actually, the table that we have in production looks very similar to the one I showed here, and we have like a bunch of services that push this data, and we just take chunk of this data and just push it into that table.
using like pushing in the same table?
Yes, yes. We push into that table, and at the same time we do the rollup from that table. We actually do that in the same transaction because all our inserts are for given apps. We just do that in parallel. And so we do the copy. We begin a transaction. We do the delete. We do the copy. We call the function to rollup, and we return.
So no performance hit on that?
No. The performance hit that obviously to get to that point, we use the optimization I showed about like asynchronous commit. The only index that we use, actually the one I showed in the slide, we have one index on the app ID, and we have one index on the timestamp. That's it. And we actually have a pretty small coordinator. So the insertion with Citus, all the data goes through the coordinator, and then it gets routed to the right shard. In our case, the coordinator is actually not that big. I think it's a 4-core machine. It's a C4 X large machine, I think, and we don't have any issue with that. Yes?
I have two questions. What made you choose Citus data? And my second question is the JSON. We talked about JSON data as well, right? So what is the source of JSON data?
So the two questions were what makes us choose Citus, and why? Actually, can you repeat? It's about the JSON-B, yes?
What made you choose Citus data?
Yeah. Okay, so for this one. So, I mean, for all the reason I said in the presentation, we haven't found a system where we could get this amount of performances, basically, elsewhere, especially with a hosted provider. We looked at Redshift, we looked at BigQuery, we didn't get those performances. We could probably have got those performances with Redshift, but then it would have required a different kind of architecture, and it would have required much more hardware to get what we needed. The architecture, the underlying architecture of Citus, where you can just parallelize your stuff and do those rollups very efficiently, the fact that you have all those Postgres extension that you will not be able to have, say, on Redshift, that provide those sketch algorithm, HLL, top N, makes it for us very cost-effective to run this kind of workload on Citus. Sorry? Scaling? Yeah, and also for scaling. So adding a node on Citus is just you adjust a slider and you rebalance your shard, and that's it. So as someone that needs to maintain the system, I like that I don't have to do too much. Yes.
Second question was your JSON data.
Yeah.
So what was your source of JSON data? Was it formatted, or is it?
In the JSON-B that I saw, that I show.
The question
Yeah, so the question is where does this come from, right? The JSON B here. This is the result of the disaggregation, this basically. The top-end API takes all our text data and extract the tops from that, and it creates this structure where you have all the top values with their frequency attached to it.
So did you use the foreign data wrapper?
No, that's I mean, there is an extension, top-end extension, but JSONB is supported out of the box. I mean, it's a native type of Postgres. Yes.
So how many number of requests per hour you get?
So the question is how many number of requests do we get per hour? So there are two things. There are the write and the insert. The write, it's basically so we insert by batch. We do maybe 10,000 transactions every 5 minutes. And the read, so we have roughly 10,000 applications into the system, but the number of QPS is actually not that high. We do maybe, we are in the lower single-digit QPS, maybe 3-4 QPS. The system is very tailored to optimizing this insertion and aggregation. We actually don't need that much resources to serve the read.
Any monitoring tools?
Sorry?
Monitoring administrative tools, what did you use?
Well, you can use everything that supports Postgres to monitor. We use APMs from Datadog, for instance. But basically, anything that supports Postgres will likely work with Citus. Yes.
It might be a little off topic, but could you speak to how you organize the rollup processes? Are they called from some cron or?
Yeah, so this is actually, so the question is how do we organize the rollup process? How do we instrumentalize it? We actually iterated on this a few times. The first time what we did was we were pushing all the data into Citus, which was an independent process. And then we basically had a cron that every 5 minutes will take whatever was pushed within the last 5 minutes and run the rollup on that. And then we move into a more distributed way of doing it, where every insert actually do the insert and do the rollup for that specific tenant, which means that the good thing is that we parallel that a little bit better. And if, for instance, a worker dies, the customers on that worker will be affected, but not the other one. So we have a cron that we have. So this is done at insertion time. Our job do this atomically, and then what we do is every day we have a cron that takes the data that is old enough, and we do the daily rollup basically. And we keep a state that tells us when was the last daily rollup, so we can always restart it whenever we want.
Thank you very much.
Yes.
Just on this one. So is your loading raw data on daily basis?
We load raw data. Yeah. So how often do we load data? Yes. So we load data that are coming from logs from all our search servers. So in our case, this is done on an ongoing basis. We do 10 billion rows per day, but basically we do it on a minute by minute basis, basically.
So for the API, the real-time API, what's the payload size?
So the question was, what's the payload size for the real-time API? You mean the data that we return from the? It's really pretty small because at most when we return tops, a design decision that we made was that our tops won't return more than 1,000 rows. So we return at most 1,000 rows basically from the system for each query. One more.
In terms of disaster recovery, so probably it's on this one that was related to data records, but how you manage that?
So the question is about disaster recovery. So if a node goes down, it will be brought back automatically by the Citus cloud. everything is backed up. We can do point-in-time recovery. We can do whatever we want at this point. There is a feature, we actually don't use it, but there is Citus provide a high availability mode. Basically, you have your cluster and you have a copy of that cluster basically running next to it, and if something happens, you just fail over to the other one. Yeah, we don't do anything very specific here.
So this is cloud-based?
Sorry?
Is it
Yes, this is cloud-based. We use the cloud offering of Citus, so we don't manage the system ourselves. All right. Well, thank you.